Thank you all for being here. I'm Ángel del Pino, and I will present you a very brief overview of my ongoing PhD thesis. It's being supervised by Professor Sánchez Arriaga, and it's been developed within the frame of the ESA project of bare photovoltaic tether and the European Commission project of ETPACT, that it will be mainly focused on a technology demonstrator about electrodynamic tethers. I will not go into much detail about this ETPACT F project because my colleagues Gasem and more particularly Sergio will give you more details later on. But I would like you to know which technology will be demonstrating this satellite. It will be an electrodynamic tethers, and electrodynamic tethers in space are also a system that could obtain energy in order to move the satellite without using propellant. So this is how it works. It will be a very long conductive wire that will flow a current, and thanks to the Lorentz force, it will generate a force that will actually move the satellite. First of all, in the 60s, they were using active electron collectors and emitters to capture and to emit back these electrons in the plasma. But with its development, those systems came more ideas to be more passive. So that's, for example, where the bare concept tether appears. So you can actually collect electrons with the bare tether itself in the space with the lower function for expelling it. And now we would like to enhance this performance using photovoltaic cells panels on top of the tether. So how it will be? It will be like in this tether we will add solar panels on top of this. You can have here an idea. This is a very thin solar layer film, about 40 microns thickness and 2.5 centimeters wide, and it will be placed on top of the electrodynamic tether that will be a tape. That's what we started developing for the ESA project. Some colleagues from Germany, they were focused on the electrical design of the photovoltaic cells. The people from Italy were focused on the mechanical part of the tether, because you can see here that it can roll up, it's very flexible, which is very important because ETPAC-F will be a half a kilometer long tether, and it will be located into a 8 EU CubeSat. So you really need to wind up the entire tether in order to fit in the CubeSat. So here you can see a cross-sectional view of the tether, and of course we won't be covering the entire tether up. I will speak more about that later. But we will distinguish two different sections, one that is fully bare and another that will be bare and photovoltaic. This is important because from the bare tether you will be collecting electrons in both sides, but it's not the case for the photovoltaic cell. And this is very important, and in the figure C you can also see 2 points that are called B1 and B2. These are the zero bias point. Electrodynamic tethers, as a difference of electrostatic tethers, do not have a constant voltage and current all along the tether. The voltage and current changes, and these points is where the voltage goes to zero. And these are very important because there's no electron collection and the equations change. And for my case, what is new is that we can have a second bias point in the tether. We can have, on the one hand, one single bias point in the bare segment or another in the photovoltaic segment. We can have both of them or do not have none. So first of all, we started computing the mathematical model. We developed the semi-analytical equations, and we obtained the the voltage at current profile that I was mentioning before, with 0 bias point, 1 bias point in the bare segment, in the photovoltaic, and in the case with 2. Also, we have been able to distinguish how the system can change in these regimes, because it's not static. It can change because of the ambient condition of the satellite. As I was telling from the beginning, we will not be covering the entire tether, because if not, we will be losing some electron capabilities of the system. Therefore, there is an optimum value, and you can see here the optimum curve, and this black line represents the optimal values for different efficiencies. But for all of them, you can see that from the beginning, we're in fact enhancing the performance, and we are in a weight range of this optimal value. So this is great for us. And moving on to more results, we have also coupled these electrical models into the BETSMA software, which is a emission analysis software developed mainly by my supervisor. We have integrated the photovoltaic tether system, and we can observe here how from 0 meters, which is in green,
Angel,
5
you
meters.
have consumed your 5 minutes already.
Okay. 3 meters in red, in blue, sorry, and in red, the deorbit time for 10 meters, and we can observe that the deorbit time is getting reduced by adding only a small amount of the photovoltaic cells. Also, part of my job is being done on CENER, that we are actually building and assembling the satellite that will demonstrate the electrodynamic tether technology, and I mainly my work there is mainly focused on the electric ground support equipment that will test that the software of the satellite is working correctly, and I will also implement the tether simulator. Up to now, I have also done some dissemination. I've been in a congress in Bertinoro, in a workshop at ISA, and we are preparing also the first paper with all these results that I was telling you before. So that's all from my side. Thank you very much. Do you have any questions?